Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we explore a quiet idea with a big reach: how Jupiter, the giant of our sky, helped build the solar system we know. In simple steps, we will see how a young sun sat inside a wide disk of gas and dust, how a baby Jupiter grew beyond the frost line where ices could survive, and how its strong pull-shaped orbits moved rocks, mixed dry and wet worlds, and steered many visitors toward the inner system and away from it. Settle in, relax your shoulders, and let's begin. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. Long before Earth was a blue world with clouds, the sun was young and wrapped in a broad, thin disk made of gas, dust, and ice. Think of a flat fog that circles a small, bright lamp. Near the lamp it is warm, so water turns to vapor and dust grains are bare rock and metal. Farther out it is cold enough for water, carbon dioxide, methane, and ammonia to freeze onto grains, turning them into frosty beads. This fuzzy border where water can stay as ice is often called the frost line or snow line. Beyond that line, each tiny grain carries not only rock but also ice, so it is bulkier. Bulkier grains collide and stick a little better. Over many orbits, they grow into pebbles, then boulders, then mountain-sized bodies called planetesimals. Beyond the frost line, there is also more total material because the gas carries a lot of light elements that love the cold. More solid stuff means faster growth. In that rich cold zone, the seeds of a giant planet had a head start. Now think about how a giant like Jupiter forms in this disk. A simple path is called core accretion. First, a rocky icy core grows by eating nearby planetesimals and sweeping up pebbles that drift inward through the gas. When the core becomes several times the mass of Earth, its gravity is strong enough to start pulling in gas from the disk. At first, the gas envelope is small and warm. As the core keeps growing and cooling, the envelope thickens. A tipping point comes when the envelope's mass matches the core's mass, and gas begins to fall in much faster. The baby giant's air becomes most of its size. Because the disk still has plenty of hydrogen and helium, and because the clock is ticking before the young sun's winds blow the gas away, timing matters. Jupiter likely formed early, while there was still a thick, gassy blanket to drink from. As Jupiter grew, it did not sit in empty space. It sat in a river of gas that flowed slowly inward toward the sun. The new giant's gravity made waves in that gas like a boat makes waves on a lake. Where those waves grew strong, they opened soft gaps in the disk. Gas still slipped through, but the pattern changed. Pebbles drifting inward could pile up at edges. Small bodies felt drag from gas and gentle kicks from gravity at the same time. In this way, even before Jupiter was finished, it was already shaping the growth of other worlds by changing the traffic in the disk. Inside the frost line, where the inner planets formed, dust stuck to dust in warm, dry conditions. Those rocky seeds were smaller at first, and their growth now had to happen with a giant neighbor stirring the outer lanes. You can picture the early solar system as a busy, quiet workshop. The sun shines weakly through the gas. Tiny grains bump and stick. Pebbles drift inward like snowflakes in a breeze. Clumps form and break and form again. Far out, a large core of rock and ice grows faster than the rest and begins to pull a thick coat of gas around itself. That is Jupiter's start. Because the giant formed early and far out where ice helped, it became the biggest planet and kept that title. Its deep pull would soon write rules that the rest of the system still follows today. Paths would be cleared, gaps would appear, some worlds would be fed, others would be starved. Through simple gravity and timing, Jupiter began to act like a quiet foreman on a very large building site, not by giving orders, but by setting the shape of the floor where everyone else had to move. Jupiter's early presence also mattered for temperature and chemistry. Regions near the frost line can trap water-rich bodies, while just inside the line, drier material builds. With a giant stirring the boundary, wet and dry stuff exchange places more often. That mixing becomes important later, when water-bearing rocks from beyond the line find paths toward the inner system. The idea that Earth's water may have come in part from such outer belt rocks is tied to these early patterns. Jupiter did not pour oceans onto Earth by itself, but by changing orbits and making safe and dangerous lanes, it helped decide how often wet messengers could reach our warm zone. Even at this first step, with most of the buildings still ahead, the giant's shadow falls over everything. A young sun, a cold ring where ice can live, and a growing core that becomes a gas giant. This is the quiet start to Jupiter's long shaping role. Once Jupiter's gas envelope swelled, its pull reached far. The new giant did not smash everything. Gravity is mostly gentle and acts at a distance like a steady hand on a turntable. But over many orbits, a steady hand can change the dance. First, Jupiter began to carve out a low-density lane around its path. In that lane, small bodies were either swallowed by the giant, flung to new orbits, or nudged into safer zones. Near the giant, gas drag and gravity together moved pebbles into traps where they could be eaten by the planet or by smaller seeds in resonant orbits. A resonance is a simple rhythm, like two dancers whose steps lock so that one makes two turns while the other makes one. In space, when a small body orbits the Sun exactly 2 times for every one of Jupiter's orbits, that is a 2-to-1 resonance. The pull adds up on a regular beat, and the small body's orbit stretches or shifts until it leaves that rhythm. The asteroid belt today shows gaps at such resonances. Those empty lanes, called Kirkwood gaps, are scars of Jupiter's steady tug. Jupiter also set limits on how big the inner rocky worlds could become. If the disk had been quiet and smooth, pebbles and planetesimals might have fed a super-Earth or two near the Sun, larger than our Earth. Instead, Jupiter's presence stirred the outer supply and broke up the smooth inward drift of pebbles. Some material was scattered outward, some was ejected entirely. Some was held in resonant rings. That chaos cut off the easy flow of building blocks into the inner zone. The result, over millions of years, is a set of smaller rocky planets, rather than 1 or 2 giants hugging the Sun. This may be one reason our inner system looks different from many exoplanet systems, where large rocky worlds sit very close to their star. Jupiter acted as a gate that both allowed and blocked, handing us a particular menu of parts to build with near the Sun. Another quiet effect was on Mars. Mars is small compared to Earth and Venus. One simple reason may be that Jupiter robbed the region just beyond Earth's zone of material at the right time. The giant's tugs and the gas drag moved planetesimals onto eccentric paths that crossed many lanes. Collisions there became more violent and less efficient for growth. Some seeds were tossed inward, where they either fed the inner planets a little or got swept into the Sun. Others were pushed outward toward the forming asteroid belt. Mars grew, but not as much as Earth and Venus. Its pantry was emptier, its neighborhood noisier. Again, no single act did this alone. It was the steady background of Jupiter's pull working with gas drag and collisions. Jupiter's reach extended beyond rocky orbits too. It guarded a pair of stable regions 60 degrees ahead of and behind its path, called the Trojan points. At these places, gravity from the Sun and Jupiter balances so that small bodies can share the giant's orbit. Many asteroids live there today. Their presence tells of capture during growth and migration, when Jupiter's mass and path were changing and small bodies were everywhere. The Trojans are a museum of early pieces saved by the giant's geometry. They did not shape the inner planets directly, but they show how a single heavy neighbor can hold onto a cloud of leftovers that would otherwise drift away or fall into the fray. As the gas disk thinned, friction with gas weakened, but Jupiter's gravitational timing remained. Resonances in and near the asteroid belt kept sculpting that zone, clearing some orbits and crowding others. Bodies that wandered into strong resonances had their orbits stretched into ellipses that took them toward the inner system or flung them outward. Over long time, this slow sorting changed the belt from a mass of builders into a leaner ring of survivors. The belt did not become a planet partly because Jupiter would not let it. Whenever enough mass gathered, resonances stirred it apart. What survived were families of rocks with many gaps between them and a wide range of compositions, from dry, metal-rich types closer in to water-rich, carbon-rich types beyond. This mix matters for Earth because it set the shelf of supply that impacts could draw from later. By the time the gas was gone and the disk turned clear, Jupiter was the stable anchor of the outer system. It had set rhythms that still run. It had thinned lanes that still look empty. It had leaned on zones that still hold small worlds in balanced points. In a system built by countless tiny hits, that calm, steady leaning counts as a major force. A giant need not move fast to change a world. It only needs to be there early, be heavy, and keep time. For many years, people pictured planets forming where we see them now. Then we found large hot Jupiters around other stars, sitting far closer to their suns than Mercury is to ours. That told us something important. Planets can move after they form. In gas-rich disks, a giant planet can trade momentum with the gas and drift inward or outward over many thousands to millions of years. This slow drift is called migration. It is not a jump. It is a gentle slide driven by the pull of spiral waves the planet raises in the disk. Whether the planet moves in or out depends on details of those waves and on the disk's structure. When another giant is nearby, the two can lock in a shared rhythm and move together. One simple picture for our system is called the Grand Tack. The name comes from sailing. A boat tacks when it changes direction across the wind. In this idea, Jupiter formed beyond the frost line and began to drift inward while the gas disk was still thick. As it moved closer to the Sun, it stirred the inner zones and pushed material around. But then Saturn, which was forming farther out, grew large enough to catch Jupiter in a shared resonance. Locked together, the pair reversed direction and moved outward for a time before the gas finally thinned and migration slowed to a stop. If this happened, Jupiter may have reached inward to about where Mars orbits now, then turned back out to a place near its present home. This inward then outward path would have strong effects. On the way in, Jupiter would have cleared and stirred the inner disk, starving the region where Mars would later grow and helping explain Mars's small size. It would also have pushed some material inward to feed Earth and Venus with fresh supplies, and pushed some outward into the belt, seeding it with a mix of dry and wet bodies. On the way back out, Jupiter and Saturn would have reshaped the belt again, leaving behind a ring that is mixed in composition and low in total mass. This helps explain why the outer belt holds many dark, water-rich asteroids, while the inner belt holds more metal-rich, drier ones, and why both types exist side by side today. The Grand Tack is a simple, testable picture that fits several odd facts at once. Mars's small mass, the asteroid belt's low mass and mixed types, and the lack of super-Earths near our Sun. It is important to say what we know and what we are still testing. Migration of planets in gas is widely supported by theory and by hundreds of exoplanet systems. The Grand Tack is a clear way migration could have worked here, and it reproduces several features of our system when modelled. But it is still a model. The exact distances and timings are under study. Some versions show less inward reach, some show different speeds. The core idea remains useful. Jupiter did not need to sit still. It could have shaped the inner system twice, once on the way in and again on the way out, with Saturn as a partner in the second half. If you imagine the disk as a shallow lake and Jupiter as a heavy skater, migration is like the skater pushing gentle waves ahead and behind as they glide. Those waves push back. If a second skater falls into step behind, the pair can lock arms and slide together at a new pace. While they travel, ripples spread and rearrange leaves on the ice, clearing streaks here and making piles there. When the ice finally stiffens, the disk gas goes away. The leaves show the path the skaters took. In our sky today, the asteroid belt's gaps and mixes, Mars's small mass, and Jupiter's stable seat can be read like those leaves. Whether Jupiter tacked exactly as the model says, or only moved a little, the lesson holds. The giant's motion was another way it built our system, not by adding bricks, but by setting the ground rules during the build. Between Mars and Jupiter lies the asteroid belt, a wide ring of small worlds. It is not a crowded stream of boulders. It is mostly empty, with islands of bodies separated by wide gaps. Its present state is the result of billions of years of steady shaping, much of it by Jupiter. The belt began as a region with enough solid material to build a planet. That planet never formed. Jupiter's gravity stirred the zone and kept the speeds of collisions high. When bodies strike at high speed, they shatter more than they stick. Growth stalled. At the same time, resonances with Jupiter carved out special orbits where small bodies were pulled on a regular beat. In those orbits, time and tug stretched paths into long ovals that crossed other lanes. Many bodies there were kicked inward toward the sun, or outward beyond the belt. Over long time, the belt lost mass and gained empty lanes. The Kirkwood gaps, which line up with simple resonances like 3:1, 5:2, and 2:1 with Jupiter, are fossils of this slow clearing. Jupiter did more than remove. It also mixed. The inner part of the belt holds more bright, metal-rich and rock-rich asteroids. The outer part holds more dark, carbon-rich, water-bearing asteroids. That gradient makes sense if the inner belt formed from warmer material and the outer from colder material. But the belt is not cleanly layered. There are dark objects closer in and bright ones farther out. This scatter likely came from Jupiter's early stirring and possible migration. As the giant moved and as resonances swept across the zone, groups of bodies were pushed inward and outward, dropping outsiders into new neighborhoods. The result is a blended shelf. That blend mattered for Earth. When resonances and small nudges sent belt objects inward later, some of them were water-rich and carried carbon compounds. Impacts from such bodies could deliver part of Earth's water and organics. Not the whole ocean in one go, but a steady rain over long time. Some families in the belt show signs of old breakups. A large body shattered and left fragments that share similar orbits and compositions. Jupiter's steady tug helped set the speeds in those breakups by keeping typical relative velocities higher than in a calm disk. These families are another archive of the system's building years. By studying their ages and types, we read back into the time when giant tides and resonances ruled growth. Even today, Jupiter keeps feeding the inner system from this ring. When a small rock's orbit slowly changes due to sunlight pressure and heat re-radiation, a gentle effect called the Yarkovsky drift, it can slide into a resonance. That resonance then lifts its eccentricity until it becomes a near-Earth asteroid. In this way, Jupiter is part of the long conveyor belt that sends small visitors across Earth's path. There is a quiet balance to the belt that suits life on Earth. Too much mass, and a planet might have formed there, changing the map of the inner system in ways that could have starved Earth of material or thrown it too many big hits. Too little mass, and there would be fewer water-bearing messengers and fewer small impacts to stir geology and feed chemistry. Jupiter's early and ongoing shaping left a middle case, a belt that is thin enough not to become a planet, mixed enough to hold many kinds of rock and ice, and active enough to send us a sample now and then. When you see a meteor on a clear night, you are watching a tiny note from that zone burn up. When a sample return mission visits a small asteroid, it reads the diary of a place Jupiter kept from becoming a world and turned instead into a record shelf for the whole system. The belt structure also keeps time. The positions of its gaps and the spread of its families help test models of how Jupiter and Saturn moved. If the giants shifted quickly, resonances would have swept across at certain speeds and left certain marks. If they shifted slowly, the marks would differ. By comparing the belt we see to the belt our models predict, we refine the story of the giants' paths. In this way, the belt is both a shaped product and a measuring stick. It was built partly by Jupiter, and in turn it tells us how Jupiter did that building. A quiet ring of rocks between two planets turns out to be one of the clearest mirrors of the solar system's deep past. When Earth was still growing, it sat inside the frost line, where heat from the young sun kept water as vapor. That means the rock that built Earth started out mostly dry. Yet today our planet holds oceans, ice, and water locked in minerals. A simple question follows. Who carried the water in? The best suspects are small bodies from cooler zones beyond the frost line, where ice could form on grains. Many of those bodies are what we now call carbon-rich asteroids. Their minerals still carry water and simple carbon compounds. The quiet hero in their travel story is Jupiter. By the time Earth was assembling, Jupiter's steady pull had already carved gaps and set up rhythms in the asteroid belt. Those rhythms, called resonances, are places where a small body circles the Sun in a simple beat with Jupiter, like 3 laps for every one of Jupiter's. At such beats, the pull adds up and slowly stretches the small body's path into a longer oval. Over thousands to millions of years, that slow stretch can change a safe belt orbit into one that crosses Mars's lane, then Earth's. When that happens, the small body can collide with a growing planet and deliver its cargo of water and carbon. In this way, Jupiter did not throw buckets at Earth. It opened doors and tilted ramps so that cold messengers could roll inward on their own. Another quiet helper is sunlight. When a small dark rock warms on one side and cools on the other, it can, over years, feel a tiny push called the Yarkovsky effect. This slow push drifts the rock inward or outward until it slips into one of Jupiter's resonances. Think of pebbles sliding down a very shallow slope toward marked grooves that join a river. The marked grooves are the resonances. The river is the path toward Earth-crossing orbits. Once inside a resonance, Jupiter's rhythm does the rest. The rock's path stretches until it meets the inner planets. Many will miss, some will hit. Over long time, enough will hit to matter. Clues that this quiet conveyor belt really fed Earth come from the chemistry of our water. Water is made of hydrogen and oxygen, but not all hydrogen is the same. A heavier form called deuterium appears in tiny amounts. The ratio of deuterium to normal hydrogen in Earth's oceans matches well with the ratio in certain carbon-rich meteorites that fell from the asteroid belt. It usually does not match the ratio in most comets from the deep cold far beyond Neptune. That suggests much of our water rode in on water-bearing asteroids, not mostly on long-period comets. Jupiter's part in that match is simple but central. It shaped the asteroid belt, created the doors by which rocks enter near-Earth space, and kept that flow going for billions of years. Carbon compounds likely came the same way. Some meteorites carry amino acid building blocks and simple organics. A rain of such material during Earth's youth would have fed surface chemistry and early ponds with ingredients needed for life. Jupiter did not write the code of life. It helped stock the pantry. It did so by setting up long-lived traffic rules in the belt, rules that made sure a small but steady trickle of water-rich and carbon-rich bodies crossed Earth's orbit. In a solar system without a giant in the right place, that trickle could have been weaker, or wild swings could have blasted the inner system clean too often. Our case sits between those extremes, not too dry, not too violent, thanks in large part to Jupiter's quiet tug on the cold shelf beyond Mars. Rocks on the Moon keep time like pages in a book. When the Apollo crews brought samples home, some dates clustered around a point roughly 3.9 billion years ago. For years, many thought this meant a sharp spike in impacts then, a late heavy bombardment. Later work showed the story may be more spread out, with several long episodes. Even so, a broad idea remains useful. The outer planets likely changed their orbits early on, and that reshuffle sent many small bodies inward. Jupiter sits at the center of that tale. One clear, simple picture for the reshuffle is called the NICE model, named after the city where it was shaped. In this view, the giant planets began closer together, with a wide disk of icy bodies beyond them. Over time, slow pushes from countless tiny gravity tugs moved the giants into new rhythms. At some point, Jupiter and Saturn crossed a key beat called the 2-to-1 resonance, where Saturn made one lap for every two of Jupiter's. That crossing changed the shape of their orbits and stirred Uranus and Neptune outward. As the ice giants moved, they ploughed through the disk of small bodies, flinging many inward and outward. Some of the inward swarms struck the Moon and inner planets. Some were captured into new homes. Some were thrown out of the solar system entirely. Through all this, Jupiter acted both as hammer and broom. It pumped energy into passing bodies and also swept many away for good. Why does this matter for how the inner planets ended up? Because a rain of impacts can strip atmospheres, reset surfaces, and change spins and tilts. If the spike was sharp, it could have been a hard season for early life. If it was spread out, it may have been a series of hard winters rather than one great storm. Either way, Jupiter's role as the heaviest actor means it had much to say about the number and paths of the visitors. It set the lanes that fed the inner system during and after the reshuffle. It also helped park some bodies in safe harbours, such as the Trojan swarms and the outer belt, leftovers from a time when orbits were still settling. It is important to keep our claims calm. The exact shape and timing of this bombardment are still studied. Some lunar dates reflect the sites chosen and the heat that later events added to rocks. New samples from other worlds may change the curve, but nothing changes Jupiter's central part in any version. Its gravity worked with Saturn's to shift the tune of the whole system, and that tune sent small worlds across the inner lanes. You can think of the early solar system as a music room where two large drums slowly found a shared beat. When they hit that beat, the strings and smaller drums responded. Some snapped, some rang, some quieted. The notes we hear today in crater counts and asteroid families fit a story where Jupiter helped strike the beat that reshaped the room. You often hear that Jupiter is our shield, guarding Earth from deep space threats. There is truth in that, but the full picture is richer. Jupiter reduces some impact risks and raises others, acting as both shield and slingshot. For long-period comets that fall in from the far edge of the solar system, Jupiter's pull is a strong filter. Many of these comets pass near Jupiter and are either thrown back out on paths that never return or captured into shorter paths that quickly lead to new encounters and ejection. In this way, Jupiter prevents many of the largest, rarest, most energetic visitors from ever reaching the inner zone more than once. That is the shield part. Now the slingshot. Bodies that start in the asteroid belt or in the Centaur region between Jupiter and Neptune can become near-Earth objects because Jupiter's resonances stretch their orbits. Jupiter also feeds a family of comets called Jupiter family comets. These have short periods and are guided by the giant's gravity into paths that cross the inner planets more often. So while Jupiter blocks many large, deep origin comets, it also helps create a steady population of smaller, more frequent crossers. For Earth, the net effect is not a simple decrease in all impact rates. It is a shift in the mix of what hits us and when. The rarest monsters from deep space are rarer still because of Jupiter, but small and mid-sized bodies stay supplied. This balance may be good for life. A planet that faces constant giant impacts struggles to keep oceans and air. A planet with no small impacts might miss delivery of certain elements, and the periodic stir that helps geology and biology restart after lulls. Earth's record shows long, quiet spans, marked by rivers and soils, broken by smaller resets and a few very hard hits. Jupiter helps set that pace. It prunes the most dangerous deep space comets. It maintains the conveyor belt of modest visitors from the belt. It also acts as an exit door. Many objects that wander into near-Earth paths are eventually kicked by a chain of encounters into Jupiter's reach and then flung outward or into the Sun. In this way, the giant not only feeds near-Earth space, it also cleans it. Even famous events show the two faces. The dinosaur-ending impactor was likely a mountain-sized asteroid from a family in the belt that drifted into a resonance and then into Earth's lane. Jupiter helped open that resonance door. But Jupiter also likely prevented many far larger long-period comets from ever becoming repeat visitors. When we run computer models with and without a Jupiter-mass planet, we do not get a simple line. We get different mixes and timings. Our system's mix seems kind to surface life over billions of years. The giant at 5 astronomical units is one reason why. 60 degrees ahead of Jupiter and 60 degrees behind, there are two deep gravitational harbors called L4 and L5. In each, the pull of the Sun and Jupiter and the spin of the shared orbit balance so that small bodies can linger for ages. These are the Trojan regions, and they are packed with asteroids. Their colors and brightness suggest a mix of rock and darker, possibly organic-rich material. Many likely formed farther from the Sun and were trapped during the time when Jupiter and Saturn were shifting their orbits. In that chaotic era, paths crossed, and some small bodies wandered close enough to slide into these balanced hollows and stay. Why do the Trojans matter for the story of how Jupiter built our system? Because they are a time capsule. They preserve a sample of early pieces from several places. If Jupiter had not been massive and moving in the right way, these harbours would not be so full or so mixed. By holding them, Jupiter kept a library from the noisy room of early times. Some of these bodies may have compositions like objects in the outer belt or beyond Neptune. Others may look more like inner belt residents. Together, they record how far the early mixing went. They also prove that a giant planet can capture and keep co-orbiting companions for billions of years, a rule we now see around other stars too. These swarms also shape traffic. Bodies that lurk near their edges can leak out over time and become new visitors to the inner system. Others may be captured from passing streams, adding to the mix. The balance is not static, it is a slow exchange across ages. Jupiter is the host, and the Trojans are the guests who never quite leave. Missions designed to visit several of these bodies will read their surfaces like pages. Craters will tell ages, spectra will tell what ices and minerals remain. Densities will tell how loosely or tightly they are put together. All of this feeds the larger question: how did Jupiter move, and whom did it bring with it? Even the very presence of two great swarms at matched points tells us that Jupiter's orbit has been calm for a long time since the early reshuffle. Strong chaos would have bled these regions dry. Their fullness says the giant has held a near-circular, steady path for billions of years. That steadiness is part of why the inner system enjoys long, quiet spans. A giant that wanders late can wreck small planet orbits. A giant that settles early and stays settled becomes a stable frame around which others can live. The Trojans hang like badges on that frame, proof that the heavy mover became the quiet keeper. Jupiter did not only sculpt the space between planets, it also built a mini-system around itself. As the giant grew, it wore a small disk of gas and dust, like a tiny version of the Sun's disk. Inside that disk, the four big moons, Io, Europa, Ganymede, and Callisto, took shape. Their order is not random. Close to Jupiter, the heat from the planet and from the young disk kept water ice from lasting, so rocky Io formed first. A bit farther out, Europa kept more ice on and in it. Farther still, Ganymede and Callisto kept even more. You can read the temperature of that little disk in the ice content of the moons. Dry to wet, inside to outside. The giant's own pull set the pace. As the moons settled, gravity locked three of them into a neat rhythm. Io makes 2 laps for every one of Europa's, and Europa makes 2 laps for every one of Ganymede's. This 1 to 2 to 4 pattern is called the Laplace resonance. Each time these moons line up, they tug on each other slightly. Those tiny regular tugs keep their orbits a little stretched, which we call eccentric. A stretched orbit makes tides rise and fall inside a moon. Inside Io, the tides flex rock so hard that it melts and erupts as volcanoes. That is why Io is the most volcanic body we know. Inside Europa and Ganymede, the tides flex ice and rock enough to keep water liquid under thick ice shells. That is why Europa almost certainly holds a global ocean, and Ganymede likely holds one too, layered deep under ice. In this way, the building of a giant did not only give us rings and belts, it made ocean worlds where there would otherwise be only frozen rock. Why does this matter for the larger solar system story? Because those oceans are among the most promising places to look for life beyond Earth. If Jupiter had not formed early and large enough to build a strong disk, and if it had not kept its moon orbits in a tidy rhythm, we might not have deep, long-lived oceans under ice so close to home. The giant did not seed those seas with life. It created the engines that keep them from freezing solid. It also shielded them at times. Jupiter's magnetosphere is vast. It can be dangerous because of radiation, but it also helps deflect the solar wind and shape the space weather around the moons. The balance of energy and shielding that results is unique in our system. Jupiter's family also gave us lessons used elsewhere. When we look at exoplanets that hug their stars, we ask whether they have moon systems and whether those moons might be warmed by tides. When we look at Saturn's moons, we use Jupiter's set as a guide to tide-driven activity. The giant taught us that building a big planet is not only about the planet itself, it is about what forms around it and how those companions can become places with water, heat flow, and chemistry. things we care about when we tell the story of where life could exist. Even now, long after the gas is gone and the big moves are done, Jupiter's steady beats keep time in the asteroid belt and beyond. In the belt, you can map where bodies are scarce and see the simple fractions in the gaps: 3 to 1, 5 to 2, 7 to 3, 2 to 1. Each marks a place where a small rock meets Jupiter at the same points in its orbit, over and over, receiving a small tug at the same phase. The way a child's push on a swing adds to the motion if given at the right moment. Over many thousands or millions of cycles, those tiny pushes lengthen the orbit into an ellipse. The ellipse then crosses Mars's path, often Earth's, and the body either hits a planet, the Sun, or is kicked away. Slower beats called secular resonances work too. They do not care about where the small body is along its orbit, but about how the orbit itself slowly turns in space. If that slow turn rate matches a rate set by Jupiter and Saturn together, the small body's tilt or stretch can grow until it leaves the stable zone. These slow beats sweep through space as the giant's own orbits change with time. In this way, Jupiter and Saturn act like a pair of bass notes under the melody of the inner planets, raising and lowering the energy of small orbits without ever touching them. These quiet rhythms feed the near-Earth asteroid population. A small rock drifts under sunlight's tiny push until it reaches a resonance. The resonance lifts it into a path that crosses a planet. The planet's pull gives a new nudge. The next resonance lifts again. Step by step, the rock becomes a near-Earth body. That is why survey lists of near-Earth asteroids keep growing even as we remove some by impact or ejection. The conveyor belt never stops while Jupiter beats time. For mission planners, this is helpful. It means fresh, diverse targets appear within reach for sample return. For Earth, it means the risk is steady but predictable in kind. We watch, we catalogue, and we learn the flow. Even comets feel the beats. Many short-period comets live under Jupiter's guidance. Their orbits change in small steps at each pass near the giant. Some are captured for a while and then released. Some break under tides. Some are dropped into the inner system for a few busy years and then lifted out again. In all cases, Jupiter's size makes small changes add up in a way no other planet can match. That is the quiet math of rhythms. A small regular push beats a big, rare shove. Across the age of the solar system, Jupiter's regular pushes have done most of the shaping of small body traffic. Look at many exoplanet systems, and you will see big rocky worlds packed close to their stars. We call them super-Earths or mini-Neptunes. Our inner system does not have them. One reason may be Jupiter's early effect on the supply lines that feed such growth. In a gas-rich disk, pebbles drift inward like slow rain. If nothing stops them, they pile up near the star and feed one or two large embryos that grow fast. Those embryos then gulp gas and become close-in giants or remain as heavy super-Earths. In our disk, Jupiter likely formed early enough and pushed hard enough to interrupt that smooth inward rain. It carved gaps and set up pressure bumps that trapped pebbles outside its orbit. It also stirred the mid-disk so that many pebbles were eaten by seeds farther out or were lost. The result is that the innermost region did not get the easy, steady supply needed to grow super-Earths. Instead, several medium embryos formed, fought and merged to make Mercury, Venus, Earth and Mars. This picture connects simple ideas. Early giant forms beyond the frost line. Giant opens a low-pressure lane and pressure bumps that trap drift. Inner embryos lose their big food pipeline. The final set is smaller rocky planets rather than one or two big close worlds. Mars's small mass then fits as a side effect of Jupiter's inward stir and outward tack, which starved the zone just past Earth. The mixed asteroid belt fits as leftover material, kicked and sorted by the same moves. It is satisfying when different strange facts line up under a simple cause. Of course, nature is messy, and other factors help too. Timing of gas loss, heat from the young sun, early collisions and chance. But a calm statement holds. Without a giant early in the mid-disk, the inner system likely would have grown differently. Jupiter's presence helped keep our inner sky open and modest, with room for a temperate world at one astronomical unit rather than a chain of heavy hot planets hugging the sun. Why does that matter for life? Big close worlds often migrate and can stir the inner zone, sweeping small planets away or roasting them. A more open inner layout leaves space for a stable, mild orbit and a long, gentle climate cycle driven by slow changes in tilt and path. Earth has enjoyed that. Our climate does swing, but within wide limits for long spans, letting life hold on and adapt. Jupiter's mass and seat helped set those limits by preventing a crowd of heavy neighbors near the Sun and by keeping the largest long-range tugs steady and far away. Earth's seasons come from our tilt. Over tens to hundreds of thousands of years, our tilt and our orbit's shape and aim change slightly. These slow changes, called orbital cycles, nudge climate. Ice sheets grow and shrink. Monsoons wax and wane. These cycles are set by gravity from the other planets, with Jupiter and Saturn as the main hands on the clock. When their slow tugs line up one way, Earth's orbit grows a bit more elliptical. When they line up another way, our tilt shifts a little. None of this is fast or dramatic. It is a gentle timing system that moves the background on which weather and oceans play. Jupiter's steady orbit makes these cycles regular. If the giant wandered late or kept a highly stretched path, the cycles could have been wilder. Instead, over millions of years, the beats repeat. Ice ages come and go. Forests spread and retreat. Life rides the slow waves rather than being thrown by sudden jerks. Rocks record the pattern in thin layers of mud on old seafloors and in rings in old cave formations. We can read those lines like a sheet of music and match them to the known cycles caused by Jupiter and Saturn. That match lets us check our models and date events. It also shows that the same giant that shaped the building of the system still shapes our climate's metronome today. Some wonder if Jupiter protects Earth by holding our tilt steady. That job mainly belongs to the Moon, whose pull damps big swings in tilt. But Jupiter's background tug helps set the pace at which the tilt would change if left alone. With the Moon in place and Jupiter far out, Earth's tilt stays in a pleasant band. The two together keep the stage stable enough for complex life to spread and persist. Again, the theme repeats. Jupiter does not act alone. It acts with others, but its mass and position are the heaviest piece in the set. By giving us calm, repeating cycles, it turned climate into a teacher rather than a breaker. Over deep time, that may be one more reason a thinking species could arise to notice the giant and tell its story. Past Neptune, there is a wide, dim region of small icy worlds. We call it the Kuiper Belt. It looks like a thick ring in the outer dark, but it is not smooth. It has families, gaps, and tilted paths. Jupiter does not live there, yet its early moves helped set the pattern you see today. In the first tens of millions of years, the giant planets did not sit on perfect fixed tracks. They traded tiny nudges with the sea of small bodies around them. Think of 4 heavy skaters gliding through a rink covered with confetti. Each time a skater kicks a handful, the skater slips a little in the other direction. Over many kicks, Jupiter, Saturn, Uranus, and Neptune drifted. When Jupiter and Saturn fell into a simple shared rhythm, a 2-to-1 beat where Saturn made one lap while Jupiter made two, the whole pattern of nudges changed. Uranus and Neptune moved outward into regions crowded with icy bodies. As they moved, they pushed and pulled those bodies into new paths. Some were flung far away, some were dropped into stable pockets, some were left behind in neat rhythms with Neptune. These rhythms are called resonances. The most famous is the 3-to-2 group, where a small world orbits the Sun 3 times for every 2 of Neptune's orbits. Pluto lives in that group. The result is a belt with parts, a cold, low-tilt core of small worlds that likely formed near their present home, and a hotter, more tilted and stretched population that was stirred and sorted during the move. Where does Jupiter come in? First, by being the heaviest skater, it set the pace of the whole shuffle. When Jupiter and Saturn found that 2-to-1 beat, their change in pull on the rest made the outer pair walk outward. Second, Jupiter helped remove a large share of bodies from the middle solar system as the reshuffle played out. It threw many detoured objects away, clearing lanes so the final orbits of Uranus and Neptune could settle without constant new kicks from the inside. That made it easier for Neptune to build the resonance net that still holds many Kuiper Belt objects today. Third, Jupiter's repeated ejections of unlucky passers-by fed the population of far-flung, long-period comets and thinned the stock near the giants, which reduced later chaos. In a quiet way, the giant far inside helped make order far outside. You can read Jupiter's role in the Kuiper Belt's mix of sizes and colours. The cold classical group, which sits in a thin band, holds many small, reddish worlds that seem undisturbed. They carry the flavour of the local birth recipe. The scattered and resonant groups are more varied. They include bodies that formed in different places and were moved. That mix is a fingerprint of the sweep, and the sweep needed a heavy inner partner to work the way it did. Without Jupiter setting the timing and removing many crosses, Neptune would not have put so many objects in clean resonances, and the belt might look more even and less rich in structure. The long-term result matters for the inner system too. The Kuiper Belt and the related scattered disk serve as feeders of short-period comets. These comets can become guided by Jupiter into family paths that visit the inner system every few years. The rate at which that happens depends on how the outer store is arranged. In other words, the look of the far belt and the mood of the near skies are linked. A belt shaped by a calm outward walk under a strong inner partner feeds a steady, moderate stream. That is what we appear to have today. In this way, the ring beyond Neptune and the oceans on Earth are not strangers. The quiet pull of a giant planet, working early and at a distance, helped decide which icy seeds stayed far away, which ones fell in neat time with Neptune, and which ones could one day leave their cold shelf and head inward as small bright messengers. When you see a short-period comet, with a return time of a few years or a few decades, you are watching a traveller that lives under Jupiter's guidance. Most of these comets started far beyond Neptune. Small nudges from many tiny pulls, plus a few bigger kicks from Neptune or Uranus, sent them inward. Once they crossed into Jupiter's realm, the giant took over like a traffic officer at a busy roundabout. Each pass near Jupiter changed the comet's path a little. The changes were not random. They followed quiet rules set by energy and the shared pull of the Sun and the giant. Over a handful of visits, the comet's long path could shrink into a shorter loop that stays between Jupiter and the inner planets. Now the comet had become part of Jupiter's family. It would return often, lose ices as it warmed near the Sun, and shed dust along its path that can later make meteor showers on Earth. These rules are easy to grasp in plain words. A small body that falls from far away has a lot of speed near the Sun. A single swing past Jupiter can throw it out forever or slow it down into a shorter loop, depending on the geometry of the pass. If it slows into a shorter loop, it will likely visit Jupiter again because their paths now cross. Future passes then shave or add a little energy each time, tending toward a set of common shapes and tilts we call Jupiter family comets. This is not a tight club. Members enter and leave. Some are broken by tides. Some split when heat cracks their crust and gases rush out. Some darken and go quiet. But the family as a whole is steady across centuries because the source is steady and the shepherd is strong. Why does this matter for building Earth? Because these comets carry ices and organics that, in small amounts, may have added to what water-rich asteroids already delivered. They also bring dust. Dust is not only pretty in a meteor shower, it settles into the upper air and can act as seeds for ice crystals or clouds. Over very long time, a steady faint rain of dust and gas is part of the way the inner system breathes. Jupiter manages that rain by setting which comets stay to make many passes and which comets are sent away after one. A system with no Jupiter would have a different balance. A system with a hot Jupiter close to the star would have a very different one. Our case, with a giant at about 5 times Earth's distance, gives a moderate, regular flow. There is also a safety piece. Some long-period comets from the far cloud beyond the Kuiper Belt plunge inward on first-time paths. These are the big wildcards. If they pass near Jupiter on the way in or out, the giant often flings them so that they do not return soon. In that way, Jupiter is a filter that removes many dangerous, infrequent threats while keeping a set of smaller, more predictable comets in family paths. The result is a sky that is lively but not wild. Comets return often enough to study and to feed our dust lanes, but the rare, huge, deep origin visitors are rarer still than they would be if no giant sat in the middle lanes. That balance, like so much else in our system, owes a quiet debt to Jupiter's mass and seat. Between Jupiter and Neptune lives a changing set of small worlds we call centaurs. They are not asteroids in the dry, inner sense, and they are not yet short-period comets. Many are icy and dark. Their paths are unstable over a few million years. They are the grey in-between, caught during slow crossings from the outer stars toward the inner lanes. Jupiter shapes their fate. A centaur that wanders inward will feel the giant's pull long before it meets the inner planets. One pass may lower its closest approach to the Sun. The next may raise it. Another might tilt the path. In time, one of two things happens. Either the centaur is fed inward and becomes a short-period comet that we will see again and again, or it is lifted and flung outward or away, leaving the stage. Which way it goes depends on the exact moment and angle of each meeting. The meetings are not frequent, but over long time they cover many chances. Why does this in-between class matter for the story of Jupiter building the system? Because the middle distances are where mixing happens. A centaur can bring the chemistry of the far outer zone, including ices that formed in very cold conditions, into regions where sunlight is stronger and new reactions can happen on surfaces and in thin gases. When a centaur turns into a comet, it releases that stored story as gas and dust we can read with telescopes and spacecraft. The rate at which centaurs become comets depends on Jupiter's gates. Open the gate wide by certain alignments of the giants, and more in-betweeners cross. Close it a bit, and fewer cross. Across hundreds of millions of years, that dial has likely moved up and down, set by the slow breathing of the big planets' orbits around their average positions. Centaurs also show that Jupiter's reach is not only about gravity slings, it shapes small body lifetimes. A centaur near Saturn can survive longer if Jupiter's pull lifts it into a path that avoids close passes for a while. The same body could be lost quickly if Jupiter tips it into a series of closer meetings. Statistics of known centaurs and the way their colors and sizes are spread reflect this steady sorting. Without a heavy inner partner, the middle region might hold a thicker, longer-lived swarm. With Jupiter in place, the middle is a hallway, not a waiting room. Bodies pass through on their way to either exit or show. That keeps the supply of comets fresh and keeps the risk to the inner planets in a stable band rather than a runaway rise. There is beauty in the names here. We call them centaurs because they are hybrids. They remind us that no sharp fence separates asteroids and comets. There is a gradient, and Jupiter's calm pull keeps that gradient flowing. When you watch a comet that used to be a centaur, you are seeing a story in mid-turn, driven by a planet you cannot see in the same frame. A ring king, far away, set the meeting that made the tail you admire. That is how quiet building works in space. One large choice early on, like the mass and seat of Jupiter, writes many small stories later, like the path of a dark, icy wanderer that glows for a few brief years and lets us read the cold past in warm sunlight. When we look at other stars, we see many systems with hot Jupiters parked very close to the light, or with chains of heavy rocky worlds crowding the inner zone. Our layout is different. We have a single giant sitting far out, around 5 times Earth's distance from the Sun, and no super-Earths packed inside Venus. That difference likely traces back to the time when planets still swam in gas. In many systems, a giant forms and keeps sliding inward, pulled by waves in the gas disk until it stops close to the star. That inward drift can sweep up or toss away the crumbs that would have built small worlds near the star. It can also shake any early small planets so hard that they fall into the star or collide and leave a messy aftermath. In our case, something stopped a full inward slide. One clean way to do that is a partner giant. When Saturn grew enough to lock into a shared rhythm with Jupiter, the pair likely slowed and reversed their drift, then moved outward a bit. The gas later faded and the pair froze in place. The result is a giant not too near, not too far. What does that buy us? Space in the inner zone to build Earths and Venuses on calm paths. A belt beyond Mars that holds a mixed store of small bodies for later delivery of water and carbon. A set of slow, steady tugs from the giant that set predictable climate cycles rather than wild jolts. A moderate flow of comets and asteroids, not a flood and not a drought. When astronomers look at hundreds of exoplanet systems, they find that our kind of layout is not the most common. That does not make it special in a magical way. It makes it worth noting. Life can exist under many sky plans, but some plans demand more luck to keep a surface stable for billions of years. A far giant on a near-circular path is one of the plans that asks for less luck. It is a simple, quiet helper. There is a pleasant test here. As we map more systems, we can ask a simple question. In the systems where we find small, long-lived planets in the mild zone around the star, how often do we also find a giant at a few times that distance on a calm path? Early hints suggest there are such pairs, though our tools find close-in planets more easily than far-out ones, so the sample is biased. As our tools improve, we will learn the true count. If the pair often goes together, that will support the idea that a wide giant and calm small worlds are linked by shared early moves. If the pair rarely goes together, that will push us to find other, gentler paths to calm inner zones. Either way, Jupiter gives us the working example by which we judge the rest. It is the pattern we can touch with probes and test with rocks and ice. Other stars show us many other ways to build. Our Sun shows us one way in detail, and in that way the far giant is a quiet ally to a small blue world. Not only rocks and ice respond to Jupiter, even dust does. Space near the Sun is filled with a thin haze of tiny grains we call the zodiacal cloud. Some grains come from comets that shed dust when they warm. Some come from asteroid collisions. Sunlight pushes these grains gently. The push has two parts. One part is radiation pressure, which acts like a steady wind and can blow the tiniest specks outward. The other part is a slow brake called Poynting-Robertson drag. It works like this. As a grain orbits the Sun, it absorbs sunlight coming slightly from ahead because of its motion, then re-radiates heat evenly. That small imbalance steals a pinch of orbital energy each turn, and the grain spirals inward over thousands to millions of years. On that slow inward road, Jupiter waits. Its gravity sets up rings of safe and unsafe paths for dust, too. There are places where the grain's slow drift is paused because the grain falls into a gentle resonance with the giant, circling the Sun a set number of times for each of Jupiter's laps. At those spots, dust can pile up into faint bands that we can see from Earth with the right instruments. There are also places where the drift speeds up, because the grain is pushed away from a resonance lane by regular tugs. When a comet sheds dust, the newborn grains share its path at first. Jupiter then edits the map. Some streamers are tilted and cut by the giant's pull. Others are drawn into its family so that the dust bands slowly wrap around the Sun in patterns we can trace. Spacecraft have flown through these bands and counted more hits when passing near resonance lanes. That is Jupiter's handwriting at the finest scale. Why care? Because dust is not only a trace, it is part of how small bodies change over time. Dust darkens surfaces. Dust settles into atmospheres after impacts. Dust traces the sources of bigger bodies. By reading the dust pattern and knowing how Jupiter writes it, we learn where grains came from and how the small body traffic ebbs and flows. Jupiter also shapes dust at its own orbit. Small grains can be trapped near the Trojan regions and in other stable places, forming faint halos that move with the planet. These halos are hard to see, but they matter for future probes and for a complete picture of how light scatters in our inner sky. The same physics will apply in other planetary systems. When we take pictures of disks around young stars and see bright and dark rings of dust, some rings may be written by hidden giants setting up the same resonance traps and gates. Here again, Jupiter is our nearby lesson. By watching how one heavy planet sculpts dust in real time, we can read the rings of far systems with more confidence. At the human scale, dust lanes also tell us about risk. Streams left by comets make meteor showers when Earth crosses them. Those showers can include larger pieces that, while still small, can threaten spacecraft or produce bright fireballs. Knowing how Jupiter has bent a stream lets us predict when Earth will pass through a richer patch. That is a quiet gift. It lets us plan, watch, and learn with less surprise. From grains you can barely see to a world you can see with your eye. As a bright point, the link holds. Jupiter sets the traffic even for the finest travelers, and the inner system reads that traffic in light and in brief streaks across midnight skies. Jupiter does not only shape by gravity, it also shapes by magnetism and charged gas. The planet spins fast and has a strong magnetic field, the largest of any planet in our system. That field makes a huge bubble in space called a magnetosphere. Inside it, charged particles are trapped and guided along invisible lines. The bubble flares wide on the side facing the Sun and stretches into a long tail on the night side, like a windsock. This space weather, though it sounds far from rocks and rings, still affects how small things age, how surfaces change, and how dust moves. That means it also matters for the story of how the outer system settled into the look we see now. Start with Io, the inner big moon, which is the most volcanic world we know. Its volcanoes pour out gases rich in sulfur and oxygen. Sunlight and electric forces break those gases into charged pieces. Jupiter's magnetic field grabs them and whips them around the planet, forming a donut-shaped river of particles called a torus that shares Io's orbit. This river feeds the whole magnetosphere. It bumps into dust grains, charges them, and can sweep fine powder away from some places while piling it in others. It also rains down over the poles of Jupiter as fierce auroras, which glow brighter than any Earth aurora and pump energy back into the system. From this one restless moon, the giant's bubble gets a steady diet of fresh material that it then spreads through the space around the planet. Over long time, that spread helps thin, fragile rings, darken faces of airless moons, and move dust along special paths that match the rhythms of the field. Europa and Ganymede live in this charged sea too. Radiation there is harsh. It strikes ice and rock, breaking chemical bonds at the very top layers. That damage changes colors we see, carves very thin frosts, and may even help feed certain simple chemicals into the icy crusts. These are small changes each day, but across ages, they write gentle notes into the surfaces, like a slow etching. Ganymede has its own magnetic field inside the larger one, the only moon known to do so. Where Ganymede's field meets Jupiter's, a miniature version of the larger dance plays out. Lines connect and reconnect. Charged particles are steered and trapped. That meeting of fields creates quiet zones and stormy zones on the moon's surface, places that age at different rates. When we map those zones, we see how the giant's bubble has been a sculptor's tool as steady as gravity, just more subtle. Even the rings respond to magnetic weather. Tiny ring grains charge up in sunlight and in shadow. As their charge changes, electric forces push them up and down, forming faint spokes that glide across the rings and fade. Those spokes are the most visible proof that light, electricity, and magnetism share the job of shaping ring patterns with gravity. Dust grains near the planet also feel a slow break from sunlight, which makes them drift. Magnetic forces and ring spokes can delay that drift or guide grains into lanes where small moons sweep them up. Over time, this changes ring brightness, sharpens some edges, and blurs others. What looks like a simple bright band in a small telescope is, in close views, a living place where snowflake-sized chips answer to more than one master. Does any of this count as building the solar system? In a quiet way, yes. While gravity set the large-scale map, magnetic weather did the finishing work. It hardened some surfaces and softened others. It painted moons in patches and stripped delicate frosts from faces that looked toward the planet. It kept dust moving so that rings did not freeze into one look and stay that way. It helped sort the smallest pieces, the way breezes sort sand, into ripples and flats, even though this breeze is made of charged particles and light. The giant's magnetosphere shows us that a planet can keep working on its neighborhood long after the big building is done. It keeps the outer system from becoming a still museum. Instead, it stays a slow workshop, with the giant at the center spinning its quiet tools of field and light. When you zoom out from rings and moons to the whole solar system, another role for Jupiter appears. It acts like a heavy flywheel that steadies a machine. Every planet tugs on every other one. Those tugs make orbits stretch a little, tilt a little, and slowly turn in space. If the tugs were wild or irregular, small planets could be thrown into new paths or even ejected. Instead, for billions of years, the inner worlds have stayed in lanes that change only in slow, repeating ways. Jupiter's mass and the near-circular shape of its path are a big reason why. The giant's steady pull sets basic rhythms that other planets follow. These rhythms are gentle but strong. They limit how far the inner planets can wander. They also set the main beats of Earth's slow climate cycles, which we will return to, but the larger point here is dynamical calm. A heavy planet in a wide, almost round orbit keeps time for the whole set. Imagine a stack of plates spinning slowly on a table. Light taps can wobble them, but a single heavy plate at the bottom keeps the stack from skidding far. That heavy plate is Jupiter. Its pull acts as a background note under all the small interactions. The result is that Mercury, Venus, Earth, and Mars do not cross each other's lanes. Their orbits breathe in and out, and their tilts nod and shake, but within limits. Over deep time, that limit kept crashes between the rocky planets rare after the early era. It also kept long-term changes in sunlight at Earth's distance within bands that our oceans and air could handle. If Jupiter's path were much more stretched, or if it were much closer, the repeating tugs on the inner set could have been larger and less regular. That would not make life impossible, but it would make calm, long spans harder to keep. Jupiter also steadies the outer giants. Its slow, constant pull ties Saturn into a safe dance, and together they steer Uranus and Neptune into paths that remain apart. Early on, as we described, the big planets likely shifted and found new rhythms. Once those were set and the leftover small bodies were thinned, the system settled into a pattern that has held. The spacing of the planets, the slight tilt of their paths, and their long-term averages have not drifted into chaos. We know this by running the clock backward and forward in detailed models, and by reading the tracks in craters and in the orbits of many small bodies. A system that is truly wild leaves different fingerprints than the ones we see. This steadiness is not a brittle stillness. Orbits still evolve. Small bodies still leak from resonances for Jupiter to feed or fling away. The planets still trade tiny amounts of energy and tilt. The Sun itself slowly changes, and that also shifts the pace a little. But the main point remains. A large, well-placed giant helps the system avoid the worst forms of long-term chaos. It keeps the inner region open for a temperate world to carry seas without losing them to wild swings in orbit. It keeps the outer region from sending in crash after crash. In this way, Jupiter's mass is not only a force, it is a promise. It promises that the basic map will still be there tomorrow and a million tomorrows after that. That promise is what allowed ocean currents, climate, and life to build layer on layer without starting from zero every few million years. It is one thing to tell a simple story. It is another to show the marks that make it true. Jupiter's role is written in many places. Look first at the asteroid belt. If you plot where asteroids live by distance from the Sun, you see deep notches at exact simple ratios with Jupiter's orbit, like 3:1, 5:2, and 2:1. These are the Kirkwood gaps. They line up with places where a small body would feel a repeating tug from the giant, orbit after orbit, until its path stretched and it left. That pattern of gaps is not a guess. It matches the math of repeating beats and the result of long computer experiments that move small bodies under Jupiter's pull. The belt's low total mass is another mark. If no giant had stirred it, a planet could have grown there. Instead, growth stalled. We see family clusters of fragments around parent bodies, a sign that high-speed hits broke things more often than they built. Open a carbon-rich meteorite and you read more marks. Some hold clay minerals that formed when water soaked rock inside a small parent body. Some hold organics, and the hydrogen in some of their water matches the ratio in our oceans better than most comet water does. That is another weak but steady finger pointing to water-bearing asteroids as a main source for our seas. Why could those water-rich bodies reach us? Because Jupiter's rhythms opened lanes for them, and sunlight's slow push nudged them into those lanes. The match is not perfect in every detail, but the broad agreement between ocean water and the water in certain meteorites is hard to ignore. Lift your eyes to the sky. The Trojan swarms 60 degrees ahead, and behind Jupiter are yet another print. These are stable points only if a heavy planet sits on a near-circular path. Their crowding tells us that early chaos gave way to long calm. Their mix of surface colors hints at a blended origin, likely the result of trapping during a time of movement for the big planets. Move out to the Kuiper Belt, and you find objects locked into ratios with Neptune, like Pluto's 3:2. Those locks are easier to create and hold if Jupiter's early moves pushed Saturn the right way and let Neptune walk outward in a smooth step. The resonant net out there is a record of the whole giant family finding its final seats. Rings and spokes add another layer. In Saturn's rings, we watch electric spokes glide and fade. In Jupiter's faint ring, we see dust that likely comes from tiny impacts on small moons, then spreads under a mix of gravity, light, and charge. These small daily effects confirm that fields and light join gravity to shape the smallest pieces. And in the big picture, Jupiter's giant magnetosphere, fed by Io, shows how one world can fuel a whole local weather system in space. That system in turn ages surfaces and moves dust. Finally, there are the models that we test against all this. When we build a young solar system in a computer and remove Jupiter, the inner region often grows very heavy worlds near the Sun. The belt looks wrong. The rate and mix of near-Earth objects look wrong. When we put Jupiter in, form it early, and let it nudge a bit while Saturn grows, our virtual system looks more like the one we live in. Models are not truth. They are tools. But when many different marks on rocks, rings, and orbits line up with a clean tool, it is a strong sign that the story is in the right family. Jupiter's fingerprints are not one giant stamp. They are 100 small smudges that, seen together, make one clear hand. It helps to ask a simple what if. If Jupiter were much smaller, the inner system would have felt weaker, slower tugs. The asteroid belt might have grown a planet, or at least more mass. That extra mass would have fed more and larger impactors into the inner lanes for longer. Earth might have seen a busier sky and more resets of climate and crust. With a smaller giant, the steady pruning of long-period comets would also be weaker. More deep visitors would return on long loops. That could raise the rare, very large impact risk over deep time. A smaller giant would also hold fewer Trojans, thin the resonant gates in the belt, and send a different balance of water-bearing bodies inward. We might have ended drier or faced our water in a smaller, sharper burst, rather than a long, soft rain. If Jupiter were closer to the Sun, say at the distance of Mars, the inner system would be a different place. Its resonances would cut through Earth's zone. The slow background tugs on Earth's orbit would be stronger and likely less regular. That could drive bigger swings in our tilt and path. Our seasons and ice ages would have different beats, maybe too wild for sea life and land plants to hold stable ranges across millions of years. The belt would be thinner or gone. Mars might not exist. Jupiter's gravity would also shorten the lives of many near-Earth objects, but at the cost of making more of them in the first place, because its resonances would sit right where many small bodies could reach them. The net risk might be higher, not lower. If Jupiter were farther out, its early help in stopping super-Earth growth near the Sun would be weaker. Pebbles might have drifted toward the star more freely. One or two heavy rocky worlds could have formed inward of Venus and Earth, sweeping the inner region clean or forcing the small remaining planets into new orbits. In that case, Earth as we know it might not have formed, or it might have formed but later been pushed around by a neighbour. If Jupiter's path were very stretched rather than round, the whole system would feel a slow, strong pulse every time the giant came into its closest point. Those pulses would pump energy into the belts and into the inner planets' orbits. Over time, that could make Mars cross Earth's path or Mercury become unstable. The long calm that helped life bloom might never settle in. These are not guesses made for drama. They are plain results from the same quiet rules we use to explain our case. Gravity's reach is long. Repeating tugs add up. Early timing matters. The position and mass of the biggest planet set the background. Fine details also matter, like the drag of gas in the early disk and the tilt and spin of the Sun, but the heavy piece on the board is Jupiter. Move it, shrink it, stretch its path, or speed its drift, and the other pieces land in new places. Our real system avoided the worst extremes. It landed in a zone where a temperate world could grow, keep water, and see a sky that was lively enough to deliver ingredients, but calm enough to allow long, slow growth. That is the gift of getting the big piece about right. Hold one last picture. A wide, dim disk circles a young sun. Dust and gas slide inward. In the cool far lane, a seed grows fast, then drinks deep and swells into a giant. Waves spread from it and carve soft gaps. Pebbles pile where the waves say stop. Small bodies gather and scatter. The young giant moves a little, then with a partner, moves back. In its wake, the inner zone is trimmed to make room for 4 modest rocky worlds. The asteroid belt becomes a mixed ring, not a planet. Cold, water-rich stones wait there to fall inward later. Far outside, as the other giants settle, a distant belt of ice is sorted into families, some locked to Neptune's steppe, some scattered outward. In time, Jupiter's steady rhythm opens and closes gates that feed the inner system with a gentle, lasting stream of visitors. Its gravity lowers the odds of the rarest, worst hail from deep space. Its magnetism keeps the local workshop around it from falling still, etching rings, darkening and brightening patches, and turning moons into ocean worlds by the simple force of tides. Its mass and calm path steady the whole set of orbits so that the map changes only in slow, repeating ways. When we look around today, we see Jupiter's work everywhere. Gaps in the belt, swarms at Trojan points, the family of short-period comets that write thin dust lanes across our skies, the sculpted Kuiper Belt that sets the pattern of icy visitors, the ocean inside Europa, the volcanoes on Io, the grooves on Ganymede, the calm old face of Callisto, the slow beats of Earth's climate cycles tied to the pull of the giant and its partner, the simple fact that inside the orbit of Venus there is empty space rather than a crowd of hot, heavy worlds. None of these features stands alone. Together they say that our system was not only built from the inside out by a bright star, but also from the middle out by a quiet giant. Jupiter did not choose to help. It simply followed the rules that all masses follow. But the result, over billions of years, is a system where a small blue world could keep water, hold air, ride gentle long cycles, and grow life that looks up and understands. The giant did not make us. It made our chances better. This is the kind of help a builder gives without speaking, by placing a beam in the right spot and checking that it sits level before the rest goes up. If your eyes are heavy now, let that last picture fade into a soft map of orbits under a dark sky. Think of a slow drum keeping time far out at 5 times Earth's distance, never missing a beat. Think of cold messengers walking in through doors it opened, bringing water and simple carbon. Think of the inner air staying, the outer belt sorting, and the moons around the giant turning tides into heat and heat into seas. We live inside the work that followed. We have time to breathe and learn because the heavy piece sat in the right place. Thank you for listening. Sleep well and good night.